If you were to go back to the beginning of the universe, and from a blank canvas, you were to construct what the early days of the Milky Way galaxy would look like, would anything out there in our universe today mirror these models? First of all, the model would need to contain 5 small satellite galaxies, all of different shapes and sizes. You would need at least 1 elliptical galaxy, 1 lenticular galaxy, 1 spiral galaxy, and a combination for the other 2. Then, with all 5 of these galaxies coming together, they would need to form one larger, singular conglomerate galaxy, slowly but surely absorbing the matter of each of these 5 galaxies. Through this conglomeration, the singular galaxy would also need to feature various globular star clusters accreted by each satellite. Once these ancient objects of incredible stellar mass are fully formed together and acting as one galaxy, the galaxy will continue to collect and accrete mass as time carries on. This will happen for eternity, until either the end of the universe or another larger galaxy crashes into it. If it all sounds too good to be true, what if we were to tell you a model such as this actually exists? And no, it's not a device to time travel back to the early period of the Milky Way's galactic history. Rather, researchers assigned to the James Webb telescope have recently used information from its deep field imaging to detect a galaxy that is almost a mirror image to what we believed our own galaxy looked like in the first part of its creation, and ultimately, its existence. Let's take a closer look at the galaxy now referred to as the Sparkler, and the mysteriousness of our cosmos it could withhold. We have spoken at length in recent videos about the marvelous discoveries currently being published as a result of the launch of the James Webb Space Telescope. One of the first, and to this day, most incredible feats of science is its presentation of the deep field and the depiction of the galaxy cluster called SMACS J0723.3-7327, or SMACS 0723 for short. SMACS 0723 was the first subject of a photo taken by the Hubble Space Telescope in 2017, showcasing the deep field galaxy cluster in all of its glory. However, when comparing the old photo to the new and improved James Webb edition, you will notice the former is much darker and less detailed than the latter. The image produced by the James Webb Telescope features more objects in the deep field thanks to gravitational lensing. Much like the James Webb, we have covered gravitational lensing in multiple instances. As a brief reminder, gravitational lensing is an effect in which matter is distributed between a source of light in the background and the observer. Light bends around an object in the foreground so that it still may travel to the line of sight point on Earth. It is used to detect old, faraway objects by using another massive space object closer to our planet and magnifying the light of the background object around its high redshift edges. This then allows astronomers to detect wavelengths and the distant hidden space objects they come from that we otherwise would not be able to obtain. In terms of SMACS 0723, this is the galaxy cluster that was utilized by the James Webb in 2022 to complete a gravitational lens and reveal new and undiscovered galaxies lost in the deep field's darkness. When researchers dived deep into the data, they found a newly revealed galaxy previously undetected in the center of the deep field image. The galaxy in question immediately captured the attention of said researchers, as it was seemingly flushed within various satellite galaxies and globular clusters. Globular clusters are massive, highly concentrated star collections formed in a spheroidal shape, all together bound by gravity. However, this newfound galaxy was not simply existing alongside the satellites and clusters. Rather, it appeared to be absorbing them as it grew. It reminded the researchers of those old models depicting the Milky Way's earliest years, when it too was absorbing celestial matter of the like. Surely, another Milky Way copycat could not be forming before their very eyes. They were wrong. Enter the Sparkler Galaxy. The first information revealing the Sparkler Galaxy was published in the monthly notices of the Royal Astronomical Society by a team of astronomers closely tracking insight brought forth by SMACS 0723. These studies were handled by two experts hailing from institutions in both Australia and the United States, named Duncan Forbes and Aaron Romanowski, respectively. The Sparkler is located in the constellation called Volans, found in the southern sky. Its shape resembles a flying fish and was first depicted at the onset of the 17th century. The Sparkler differs from many of the other galaxies and objects within Valens in that it is located a whopping 9 billion light-years from Earth. When it was first detected, the Sparkler was recorded using a redshift measurement of 1.38. Using these calculations, it is estimated the snapshot of the burgeoning galaxy dates back 9 billion years ago, or just 4 billion years after the Big Bang. Of course, 4 billion might sound like a lot, but it's a relatively short time frame when compared to the rest of the universe and our understanding of time. Without a doubt, the universe looks much different today than it did back then, and astronomers will never scoff at another opportunity to look at the ancient makeup of the cosmos when it arrives. The name the Sparkler is derived from one of the galaxy's most intriguing features. Within the Sparkler are about 24 or so orbiting globular star clusters. For context, our own Milky Way galaxy is currently thought to withhold 200 or so of these same types of globular clusters, containing around 1 million stars each. However, it certainly hasn't always been that many, and predictive models suggest the early versions of the Milky Way held about as many as the Sparkler did when they were both only 4 billion years old. In order to make these observations, the aforementioned professors Forbes and Romanowski utilized both the age and the metallic distribution of half of the known globular clusters found circulating the Sparkler. These researchers noticed the ages of some of the star clusters' formation, combined with their apparent richness of various metals that are also seen in the bulge shape of the Milky Way, pose as direct evidence that the Sparkler was on the same trajectory as our own galaxy. It should be noted that not all of the globular clusters were of the same type. A few of these clusters, closely connected to the satellite galaxies merging into the Sparkler, aren't as old or minerally rich. Of course, that isn't necessarily a sign of defeat, as the early Milky Way models also predict there were smaller, weaker star clusters when the galaxy was first forming. In fact, that alone might be the biggest sign astronomers are charting a course through time to get a snapshot of what used to exist right here at home. As it stands, the 9 billion year old light we are seeing from the Sparkler indicates the galaxy is only at a mass equal to 3% of the current Milky Way. That's not to say it won't match our own mass over the next 9 billion years of cosmic time, but it does pose an observational challenge. It's hard to predict what exactly the Sparkler will turn out to be without deeper imaging. If technological capabilities here on Earth are advanced enough to lens even more light into our space telescopes, newer satellite galaxies and globular clusters can be detected within the Sparkler. Not only does this discovery of the Sparkler give astronomers insight into the aforementioned potential of a look at a young Milky Way, it also brings insight into the nature of globular clusters as well. Globular star clusters and their origins are actually quite unknown to researchers. While they understand their function within galaxies and their overall chemical makeup within the cosmos, how and why they exist in the way that they do isn't as clear. To be able to see these same clusters at the earliest stages of their existence would clarify so much about their ambiguous relationship to galaxies and the physical nature of our universe as a whole. Beyond just deciphering the mystery of globular star clusters, however, is another exciting proposition born from the Sparkler's known existence. Depending on how advanced a civilization we become in terms of our space observation abilities, there's a chance we could watch an entire solar system come to fruition within the sparkler's final form. That's not to say the sparkler is a mirror image of the Milky Way galaxy, or we're looking through a rip in space-time that gives us a look 9 billion years into our own past. In other words, the sparkler is not the parallel to the Milky Way in a parallel universe. Yet, if the sparkler is already mimicking so much of what we've already modeled the Milky Way to look like in its youth, who's to say the sparkler won't also harbor countless solar systems with planets that not only reflect the planets here at home, but new types of planets? And if we're extremely lucky, maybe the laws of physics will perfectly come together once again to form a life-harboring planet such as Earth. Again, this is all just conjecture, as the Earth and humanity itself isn't expected to live past the death of our own sun, a process which begins nearly 5 billion years from now. But at the same time, the sparkler is the perfect symbol of hope astronomers and researchers alike have in using it for so much more than satellite galaxy research. It's a window into our past, but also a window looking into our future. As long as technology continues to evolve at the pace it's currently at, and the Earth survives deep into the night, we might see the universe deliver another version of the Milky Way, another version of the solar system, and another version of ourselves.